Hey guys, coming at you today with net ionic equations and double replacement reactions. So, to review from what we did in Chemistry 1, all across the nation, Chemistry 1 students will learn these 5 reactions. And they're very helpful, those 5 little umbrellas, and I think that are easy to separate because when you look at an equation, you can identify these pretty simply. The trouble is when they go to college or when they go to somewhere else, they find out that they never use those again. These are the ones that are taught in college textbooks, and they're the ones that what chemists use today. The double replacement reaction or precipitation reaction, the acid base, and the redox reaction or oxidation reduction. These are better umbrellas to fit all of to classify our reactions because they really separate very nice and easy. And it's in the next 3 sections, in the next 3 videos, we'll be covering one of each of these at a time. And I'll just point out in section 4.4, you guys can see, I know it's backwards, but you guys can see how comically short that section is because all it does is tell you these 3 reactions. I just wanted to point that out. I think that's the shortest one in the textbook. I'm putting these slides in a different color because I want you to please don't forget these decomposition reactions. These are decompositions, and you must memorize that sulfurous acid will decompose spontaneously, automatically into water and sulfur dioxide. You may be responsible for knowing that without being prompted. Likewise, you're also responsible for knowing that ammonium hydroxide does not exist, just like sulfurous acid, because it will decompose automatically. The reason is because the hydroxide ion, this bond between the hydroxide ion and the ammonium ion is relatively weak, and the molecule will actually prefer to exist as 2 different molecules. It's a marriage destined for failure, however you'd like to think of that. A double replacement reaction is going to be 2 compounds that will react to form two new compounds. No changes in oxidation state happen, so that's going to be another video later on in this chapter. You also should know that there's going to be a driving force. Just know that there's a driving force that will allow these ions to break up. The driving force is going to be covered in a later video later on in the year. Double replacement reactions will come in 3 different flavors. The first flavor is that it will form a precipitate. That will be the solid that is formed in the product and will precipitate out. It will fall out of solution. All of a sudden, we have 2 liquids that we put together into a test tube, and now a solid has now come out. And it's kind of cool to see, and it will just now fall down to the bottom. The trick for knowing these is you have to know your solubility rules. So the solubility rules are, the first 2 are easy to memorize and easy to pick up on. The very good rules of thumb that all nitrates are soluble and that alkali metals and ammonia is soluble. Now there's other rules here that are listed, and these rules are on the back of the blue periodic table in my classroom, so they are available for reference. You need to memorize as much as you can to be able to write these precipitations, because I will not let you, in the AP test, will not let you use the solubility rules on the test. Most of the time you can get by with remembering the first 2 for sure, the first 2 rules, and I also try to remember that the halogens and the sulfates are soluble for the most part, and you can memorize the exceptions individually. And I also remember that the hydroxides are are almost always insoluble. So something like most bases are actually usually pretty insoluble. Only some of the strong bases are marginally soluble, meaning they just dissolve just a little bit. An example of this would be if we had silver nitrate and lithium bromide, we would have we would write those in our reactants, and then we would have to predict the products here, and we would have to know, we would be able to predict these two, and then we would try to look and see if there was something that wasn't soluble. I do know that nitrates are soluble, so I can definitely put an aqueous there. And then if I was told that a precipitate would form, then I would know this was the precipitate. The second flavor is that there could be a formation of the gas, meaning that that you will usually get one of these three, and they will decompose into this, like I showed you before with those decomposition reactions. So an example is if I had hydrochloric acid and potassium sulfite, these two hydrogens will now will be floating around in solution, and the potassium and the sulfites will be floating around in solution. They will now join up and make a sulfurous acid, sorry, and that will spontaneously decompose to water and sulfur dioxide, which is a gas. You should be able to smell it. Another example is if you had sodium hydroxide and ammonium chloride, you mix those two together, you get sodium chloride, salt water, ammonium gas, and water. You would not get ammonium hydroxide. You'll get to do this in the lab, and if you waft it and smell it, you can actually smell the ammonium gas coming out of it. And the third flavor is the formation of a molecular substance. Remember, molecular is the same as a covalent bond, and that is typically going to be water or acetic acid, which will now dissolve in water, or water is just still water. So you might not see evidence of it in the actual lab. So an example would be lithium hydroxide and hydromic acid. When I mix those two together, I get lithium bromide, which is soluble in water, and then I just get water. So I wouldn't be able to actually see a reaction happen. This would be a no visible reaction. Or when gaseous hydrofluoric acid reacts with solid silicon dioxide, that's a fancy way of saying I am now going to take some acid and etch glass with it, because this is glass, silicon dioxide, and then they use hydrofluoric acid to etch it, and it will make silicon fluoride, silicon tetrafluoride, and it will make water. And you might be wondering right now, how the heck am I going to actually be able to look at this on a piece of paper and figure it out? Stick with me, I'll show you. Let's learn how to write net ionic equations. Here are the three definitions of the three different types of equations. Take a second to pause and just kind of review the definitions, then we'll cue the camera. Let's learn how to do our molecular equation, complete ionic equation, and net ionic equation. Please refer to the text on pages 153 through 160 in those sections. I'm going to note where you are on the video right now so that you can see and come back to the reference of the periodic table. And your polyatomic ions, which you should have memorized, but it's helpful to have reference. Before in first year chemistry, I have given you an equation like this and I've asked you to predict the products. And I've taught you to just go ahead and look at identify the metals, which are the first terms, and to just switch the metals. And it should work out for you, right? And you would be expected to come up with this answer. And you would have potassium nitrate plus silver chloride, and you would have to use the solubility rules in the back of the periodic table just to see which ones are aqueous and which ones are solid. A lot of you had a lot of questions on it because you knew there was a lot more to a double replacement reaction than this, and you are right. Let's get on to it. This is known as the molecular equation. Here, this is the molecular equation, just like what you've normally seen. So now let's look just at our the reactants right now, and I want y'all to note that these are both in aqueous solution. So if they're in aqueous solution and they're ionic compounds, they will actually break down into different ions as soon as they touch the water and once they dissolve. And we would get these four terms that are now available in our ionic solution. They, with the aqueous terms all written here, it's a little cramped, so I'm going to go ahead and take off the aqueous terms. And now I have my four different ions that are now in my solution. Let's just say the solution is my white piece of paper, and now I have my ions all spaced out ready to go. Now these ions are free to move around and free to make any kind of combination they would like. So let's see what kind of combinations we could get. First, let's remember a rule that the precipitation reactions will have a net charge of 0. So that means is when these ions are floating around and they try to make different combinations or they start interacting with other ions, I get two positives that have now traveled on over towards each other, and now instead there are two things wrong with this. Two positive charges would not attract to each other, they would actually repel from each other. That's called Coulombic repulsion. It's the opposite of Coulombic attraction, where two like charges will repel now. Also, the net charge, if these were together, the net charge would be a positive 2, and this net charge would be a negative 2. So that's not going to work. That won't work out. So so that's not possible. These will now repel off of each other, and now we end up back where we started. And okay, so let's try another combination. What if these came around and oh nope, that's not going to work. What if these came around and I came up with something like this? Okay, alright, so I've got a positive and negative attracting now, so that's good. And now I've got a positive and negative attracting now here. Except all of a sudden, this happens. As soon as the silver and the chlorine came together, they made a solid. That's what a precipitate is. This silver chloride is not soluble in water, so as soon as they come in contact with each other and they start to attract to each other, they have now formed a solid. And once those are a solid, they are locked in. And so now they will now precipitate out and now come down to the bottom and sit down here at the bottom of the test tube or the sample. The potassium and the nitrate will now continue to float around in our solution just kind of all willy-nilly like they were before. So now these are called spectator ions. These ions here are called the spectator ions that will be important later in the near future. So I've shown you how to manipulate the molecular equation and to break up all these ions, and we had the spectator ions. So we will now show you how to do the complete ionic equation. That will be everything that was in the molecular equation just broken down into ions. So you'll have to bear with me because I can't get it all on the screen. I will first replace these with the aqueous ones because now I will have room. Unfortunately, I do not have enough room to put the plus signs in between. So you guys can imagine that there are plus signs in between each term. And then I'm working backwards just a little bit. I'm going to have the reaction arrow, and then I'm going to have what I started out with, where I had them together. Oops, I don't want that one. So this would be an example of the complete ionic equation. I have all my reactants on top and then all my products on bottom. Also, please notice that if it is in solution, it is aqueous. So the aqueous symbols, the state symbols, are still important, so we can't drop those off. So the difference between the molecular equation and the complete ionic equation is the molecular equation has them grouped together, the complete ionic equation has them broken down into ions. To show the net ionic equation, I'm going to take out this term. What I want y'all to indulge me just for a minute, and if I treated this reaction arrow like an equal sign, I would see that I would have more like a mathematical equation. Again, we're imagining that there are pluses in between our terms. So if I do that, I know that if I have two terms that are the same on both sides, I can exclude those. And if I have two more terms that are the same on both sides, I can exclude those. Now everything is different on one side or the other. So I will put the reaction arrow back in, and I will also place my metal first because that's good practice, and then I will now have room to put my plus sign. This would be an example of a net ionic equation. The purpose for having the net ionic equation is because it shows the reaction that actually happened, or the one that we actually saw. We're excluding all the potassiums and the nitrates because nothing really happened. Those were spectator ions, but these actually did contribute to the reaction. That's what we saw. We saw the precipitate form. Let's do another problem out of the textbook where we're going to take two solutions of potassium chromate and barium nitrate, and we're going to put those together in the lab and see what happens. Before we go to the lab, we'll probably want to understand what we might see. So we'll be able to make an educated guess if we break these down into ions. Notice that I kept the aqueous solutions on each one of these, and I also put the charges on each one of these. Also notice that I put two potassiums because there are two of them here, and I put two nitrates because there's two of them. So now let's combine those potassium and nitrates. This gives us an idea of where we're going to go and of the reactants for the combined ionic equation. Now let's put our plus signs and our reaction signs. So now let's really try to make an educated guess of what's going to happen when these all are floating around in solution. I know that potassium is always soluble, and it's always just going to be soluble. You know that from the solubility rules and also on the back of the periodic table, and and I know that the nitrates are always soluble as well. When the barium will come in contact with the chromates, though, those will now become a solid. Those will be our likely precipitate. So let's write that now. I have written barium chromate as a solid here so that it is represented as a precipitate, and this is the actual complete ionic equation. So let me cut that up and I will put a label on it. Here's my label, and I'm going to put it right on top of the top ones because we don't need that anymore. And this is my complete ionic equation right here. So now let's go ahead and see if we can write in the products for this one. We'll go ahead and combine these two and just still call them aqueous so we can have the products for our molecular equation. I'll scoot this down so we can put the molecular equation label on here. Now that that's done, we're pretty much ready to go, and it's easy enough to see which ones are the spectator ions now. But to get the net ionic equation, if we just cancel out all of our spectator ions. So now I'm going to scrap everything that's here, wipe it clean, and I'm going to move this up for reference. And I want to write the net ionic equation. So underneath, well, first I'm going to cross out my spectator ions. Those are the ones that appear on both sides. I have two potassiums, and I have two nitrates and two nitrates. Now my complete ionic equation, I'll still put the metal first because that's good practice. And we have now arrived at the net ionic equation. Congratulations, guys. We'll be able to do this now, and you are ready to do this in a class activity. Hey, guys, thanks for watching. I love these net ionic equations. Stick with those solubility rules. You'll be able to memorize them. Trust me, it takes a lot of practice. We'll be getting a lot of practice in the lab. All right, say goodbye. Bye-bye. Say bye-bye.